hoy tenemos el placer de tener a SARA y MICK del Departamento de Aeroespacial, que nos viene a hablar sobre su GPS lunar, proyecto del cual recibieron un premio el año pasado, me parece. Y pues tenemos el placer de tenerlos aquí contándolo. Así que muchas gracias, SARA y MICK.
Hello. The talk is going to be in English. I'm sorry because well, he's from the Netherlands, so but you can ask in Spanish after the talk, and he more or less understands. But to do the speech a little bit more fluid, it's going to be in English. So I hope that's not a problem. So it's on, no? Okay, so let's start. So this is our project. So as he has presented us, we are part from the aerospace group, from the electric propulsion and plasma team. And what we are presenting today, it's part of a project that we did last year. That we really enjoyed doing this project, and we think that maybe you will find it interesting. So, okay. Let me put the topic in context. Like last year in April, May, there was a call from the Electric Propulsion Rocket Society that they were, it was named Young Visionary Paper Competition. And basically what they were searching for, for young researchers, being able in somehow looking outside the box and try to submit an original work, visionary, futuristic work concerning electric propulsion, but the most technical as possible. So I'm gonna read you exactly what was the requirements. Participants are required to submit a paper and short video presentation, so there's gonna be a video. But addressing the theme, the future of electric propulsion. Okay, so this is, as you see, a very open question, the future of electric propulsion. So you could be thinking in exotic kinds of thrusters, missions, crazy missions, space missions, whatever. We, the four of us, because well, I haven't said we were four in this group, but here we are only Mick and me. We decided to start trying to answer to this question: where will electric propulsion have the most impact in the next decade? So in order to answer this question, I'm going to do a little bridge, okay, a small bridge, and try to explain in very general terms what's electric propulsion about, because I haven't said anything about it. So if you try to Google electric propulsion and look in the Wikipedia and so, you will find this kind of definitions. Electric propulsion makes use of electrical power to accelerate a propellant by different, possibly electrical and or magnetic means. So this is it's saying lots of things and it's saying nothing at the same time. So let's try to be a little bit, let's rewind a little bit in time and just speak about general rocket science. Rocket science actually is based on a very, very simple and one of the most accepted laws in physics. It is the third Newton's law. For every action, there is an equal and opposite reaction. This is just as simple as that a car can move in the road because there's a reaction with the road. An airplane can fly because there's a reaction with the air that goes through its motors. But what happens in space? Because in space there's nothing. So there's only one answer. In space we have to carry the mass with us that's going to have this reaction force. And this is basic rocket science. So basically this means that a rocket, when a rocket is, let's say when it's ignited, it will eject some mass and then its own mass will change and then its own velocity. So just after some little algebra and applying just momentum conservation to this, we end up what we know as the most famous and most fundamental equation from rocket science. That is also known as Tsiolkovsky's equation. So, but if we have a look at this equation here, this will be the total increase in velocity. This is the exhaust velocity. And this is the ratio between our initial mass and our final mass. So when we look at it, we can try to think, but are these good news or are these bad news for science? To understand this question, let's try to see what is delta V. In space, for example, here in the Earth, if we want to go from here to Sol, whatever, we are thinking, okay, it's 20 kilometers we have to do. But in space, if we're going to go from here to here, we don't think in distances. We're thinking, what's the total increment in velocity that we have to give to our spacecraft? And the reason is very simple, because to be in an orbit in Earth, we need to have the total energy of this orbit. To be in this orbit, we need to have the total energy of this orbit. To go from here to here, we will have to give, this is a very simple schematic, obviously it's not so simple as this, but to give you an idea, just a small impulse, we go to here, and then a small impulse to remain in the moon orbit, for example. So, in other words, from a propulsive point of view, the restriction in rocket science is the total delta V, the total increase in velocity that we have to give to a spacecraft. Here, this is a very simple graph that you can find anywhere. That is basically, here is Earth, here's the Mars, here's the Moon, and this is the total delta V that you have to give to go from one orbit to another. So as you see, this is our parameter. Okay, so let's give numbers. Let's see what happens. This is the very orders of magnitude, okay, of how is this delta V from some specific missions. For example, escape from the Earth's surface, from the Earth orbit to Mars and return, and from Earth to Jupiter and return. So as you can see, if we get this one, the second one, let's go to Mars and return, it's 14 kilometers per second, more or less the total delta V that we have to give. So imagine we have a rocket that is able to give us this exhaust velocity of 4,000 meters per second. Let's do the math. It's a very simple math. We only have to divide. And we go here. You see, more or less we are in 3.5. Wow, we obtain a mass ratio of 30. This means that if we want to put 1 kilogram of payload to Mars and return, we need 30 kilograms of propellant. So as you see, this is clearly bad news for science. But some of you will think, now, okay, but you're cheating us because that's because you've put here 4,000 meters per second, but why don't we put there a higher exhaust velocity? And you're completely right. But one thing that we have to think now is, can we really increase this exhaust velocity? Let's think about a classical rocket, the chemical rocket. How is this velocity determined? The exhaust velocity of the gases. You have to imagine you have a combustion process, your gas, then you have the nozzle of your rocket. Obviously, some of you can see the answer clearly. This velocity is limited. It's limited by the internal energy of the propellant. And in reality, in rockets, in classical rockets, it's around 1,000 to 5,000 meters per second. So I chose actually a very good rocket in the example. They are energy limited. So one guy in the, some time ago, he started thinking, is there a way to increase this exhaust velocity? What forces that we know in nature? I mean, not many forces. One of them is the electric force. Could we somehow, with electric forces, try to increase this velocity? And some think, okay, yes, we can do that, but we need some matter that reacts to the electric and magnetic fields. In other words, we need plasma. And that's why, with plasma, we are just creating plasma. It's just ions and electrons and free charges all mixing around. We are able to apply electric fields and achieve very, very high exhaust velocities. So as you see, this is a great advantage because we will be able to use less propellant. But here, obviously, there's a cost. What is the cost of creating plasma and creating these electric fields? We are power limited. And this is the main, let's say, the bad part of electric propulsion nowadays, is that we are very power limited. And just to give you an example of how power limited we are, I like to put this image. This is Chang'e, the astronaut Chang'e. Probably some years ago, you will have heard in the social media, there was one news that said a plasma rocket engine may get us to Mars in 39 days. And also I remember my father showing me this, Sarah, look, this is what you do. And I was like, no ways. This is not at all what I'm doing. Is this really possible? And then you have to, if you read the small letter, it's like the small letter you never want to read in the contracts, you see, to achieve this, we need 50 megawatts of power. 50 megawatts of power. Just you can see, it's feasible. It's feasible. Let's look in the International Space Station. Do you know how much power is capable of delivering with all its solar panels deployed? 0.12 megawatts. So we will actually need 400 International Space Stations to power that monster and go to Mars in 39 days. So it doesn't really seem very feasible. It's true that if we move to nuclear stuff, then we are talking in other numbers, but that's another talk. Okay. So for us, this is more like the kind of perspective that we should have for electric propulsion, at least nowadays. With electric propulsion, basically, we can go further. But with the technology that we have available nowadays, it probably will take a while. And this is nowadays technology. So I haven't been very technical till this moment. I'm just going to put this equation. It's simple, I promise. So it's just, how do we generate thrust with these kind of thrusters? So this is just the momentum balance equation. This will be like how the momentum of ions. So how do we transfer momentum to the ions? Okay, but we have three, as we know, in nature, we have only three ways to doing this. First, pressure gradient. This is like a normal thermodynamic expansion. Okay, it's not a big deal. Secondly, electrostatic. We could put just some grids. Imagine you put 200 volts, 300 volts, whatever. You pull the ions, you accelerate the ions, and then you put like a small electron gun to make sure that everything that comes out is quasi-neutral, or it's current-free, sorry. And then the third one, this is the Lorentz force. So electrostatic, this is pressure, gradient pressure, and Lorentz force. And in terms of the Lorentz force, I'm going to introduce very, very briefly one concept that is magnetic nozzles, because it's the one that we chose for our project, and then MICK will talk a little bit more. What's a magnetic nozzle? Among let's say, how do electromagnetic thruster works, okay? Just in very general terms, let's imagine here that you create a very hot plasma, okay? You have lots of electrons and ions, very hot plasma. You apply a magnetic field, divergent magnetic field. So when you apply a magnetic field with the plasma, what will happen? The electrons will be magnetized, let's say, and they will start going around and going further, going through the magnetic lines. So there will be these electrons that are moving in the magnetic field. Then ions will see this electric field, and they will be attracted to the electrons. So this way we can more or less accelerate the plasma. It's what we call the magnetic nozzle. Okay, so in terms of thrust, how does this generate thrust? You have to imagine that when the plasma is ejected, because it's magnetized, you have lots of azimuthal currents. So at the end, the plasma is acting like a magnet. So it's like you have a thruster that is made of a magnet. And you are ejecting something that is like other magnet. So what will happen? You have this magnetic thrust. Okay, this is like very, okay. So now I can go back to my first slide and say, okay, let's answer this question. Now that you all have basic notions in electric propulsion, let's try to answer it. Where will electric propulsion have the most impact in the next decade? For us, the answer was pretty clear: micropropulsion. And let me try to now convince you why we have to go small for it, okay? Let's think in nanosatellites. Why we have to go small with electric propulsion? Well, first of all, because we can. Because some years ago we couldn't. It was not possible. Now we have the technology. Now we have nanoelectronics, we have micro power sources, we have everything can go small. Everything is going small. So why not? Okay, we can. But secondly, are there any advantages in going small? Obviously, yes. It's going to be much cheaper, much easier to build, to produce, to launch, to maintain. So we are going to save lots and lots of money. But okay, up to here you can say, okay, we can do it, it's cheaper. But in terms of performance, it is better to have micropropulsion or not. Well, let's think, for example, that you want to have a specific mission, and you have two options. You can do this mission with a very large satellite, okay? And you can do the same mission with 30 small nanosatellites. What would you choose? Well, think if something happens to the large satellite. It's game over. If something happens to one of your small satellites, you have still 29 left. So obviously, in terms of redundancy, this is going to be to have lots of reliability and feasibility to our mission, so it's good news. Okay, and even if you start thinking like, even go a little bit more ahead, you can think, what will be the impact in society when nearly anyone can build a small satellite and launch it and will be full of satellites? Well, imagine the impact in the scientific research. Just for example, you remember the Columbia accident some years ago. Imagine that they will had a small satellite just going around the spacecraft before the entering. I will be able to detect that there was a problem. Whoops, sorry. That there was a problem So maybe we could have avoided this disaster. So it will have lots and lots and wait, now it's different. Okay. So some of you probably will be thinking now, okay, I hope that I convinced you that going small is, has a lot of advantages in space propulsion, but can we go small with chemical propulsion? Or why we have to choose electric? Well, obviously, I think I've demonstrated you that with chemical propulsion, we need much more propellant. So if we need to put everything in a small CubeSat, it seems like it's not a good idea to use half or whatever of the space to use propellant. But also with chemical propulsion, we are going to have combustion processes all together with very expensive stuff that we want to move to space. So it doesn't seem like a very good idea. And also, we really don't need so much thrust, because with chemical propulsion, we obtain very high thrust, but it's not our goal. So there's no reason why going small with chemical. So now we are at the point, and this project, we were like, okay, so for us, the future of electric propulsion is nanosatellites. But we wanted to see this applied to one specific mission, or to see some numbers, to see some reality. So the next question was, where do we go? And for what? So I put some news, so let's see if this was from September last year. Moon Village, the first stop to Mars from the European Space Agency. Over 100 people could be living in a lunar village on the moon by 2040. How NASA plans to send humans back to the moon. I can continue. China's space dream. A long march to the moon and Mars. Shooting for the moon, this time to stay. So what I want to say, for us, the answer was clear. We had to go to the moon. And if we want to go to the moon, it's sure that at some point we will need some satellites, constellation that will provide us information about, for example, like a GPS, or that we've called the LPS, just to see, to move around and to be able to have a normal life in this our new home. So now my colleague Mick is going to give some specific details about this project, and I pass him the mic.
See, test, yeah, no? Is it working? Is it working? Okay. Thank you, Sarah. So we're going to the moon, and this time we're going permanently. And you can imagine that there's a very big infrastructure that goes with that. And for instance, these moon bases will be built by autonomic vehicles, and they would read, for instance, information on their position. So you can imagine that a GPS system or a lunar positioning system would be very useful for to have on the moon. So we need a constellation of satellites around the moon to determine our position. And before I go into how this constellation works and how we design one, I'll first explain a bit of how GPS works. So GPS is based on the concept of trilateration, which means that if I don't know my own position, but I do know my distance to 3 points of which I do know the position, I can calculate my own position. And that works as follows. If I know I'm a distance d away from a satellite, then I know I'm on a sphere centered around that satellite. And that's true for all 3 satellites. So I know I'm on the intersection of the first and the second sphere, which is a circle. And more precisely, I will be on the intersection of a third sphere with that circle, which leaves me 2 points, one of which will be in space, and the other one will also always be on the surface of the planet or moon you're orbiting. So since I know I'm not in space, at least here when I'm on Earth, I know I'm not in space, so I know which one of those 2 points to choose, and I know my position. But actually, trilateration is a bit of a misleading term, because you don't need 3, but you need 4 satellites. And to understand how that works, so this distance between me and the satellite, how do we calculate this? So the satellite is like a lighthouse, and instead of sending out just a beam of light, it sends a radio signal with its position coordinates, x, y, and z, and the time of transmission. And me as a receiver, I can see at what time did I receive the transmission. I know when the satellite sent it, so I know the time difference, the travel time of the signal. And since I know that radio signals travel at the speed of light, I can calculate the distance the signal traveled in this small time interval. And this is called delta x, which is the distance or the range. But in reality, my clock, of the receiver is not very accurate, and even the satellite has a small error in its clock. So what you will have actually is the pseudo range, which is the original range plus the time, the speed of light times the time offset of me and the time offset of the satellite. So in reality, the time offset of the receiver is much more inaccurate. The error is much bigger for the receiver, so we're focusing on that one. And if you write a pseudo range for for PI for satellite I, which X, Y, and Z I are the coordinates of a satellite, X, Y, and Z are my own coordinates, and I'm also left with this fraction C T offset. So you see that you now have an equation in 4 variables instead of in 3. So you need at least 4 equations to solve for this, and therefore you need to see 4 satellites at minimum to calculate your position. So when we talk about global positioning systems, there's actually a multitude of systems that we're talking about. The regular one, GPS, is the one we call Navstar. It's from the United States. There's also a Russian system, which is called GLONASS, and the Galileo system, which is European, and that will be operational hopefully by 2020. And there's also Baidu, which is Chinese, and Navic, which is Indian, and they're currently regional systems. But for instance, Baidu will also have a global system by 2020. So when you think about GPS, regardless of the system, there's always 3 segments. There's a control segment, a space segment, and a user segment. And the space segment is quite obvious. It's basically the constellation of satellites, while the user segment is anybody who has a GPS receiver. Could be your car, could be your phone, could be a ship, or another spaceship, for example. And so the user is always a passive receiver. You never send some people are confused about this. They think that your phone contacts the satellite, which is not true. The satellite is like a lighthouse. It shows that it's there by sending its signal. And you don't shout at the lighthouse, you don't shout back at the lighthouse telling where you are. The lighthouse doesn't get it. So you only receive the signal of the satellite to determine your position. The control segment consists of a network of ground stations that track the satellites, and they update the satellite positions, because usually the satellite tends to drift away from its orbit a bit. And also they synchronize the clocks of the satellites. And the communication between the control and the space segment is bidirectional, it's two-way. So since we use the speed of light to calculate the position, the speed of light is quite a large number, we need very accurate clocks on board of these satellites. As you can see here, for a time difference or a time error of 1 nanosecond, that will result in an error in the distance you calculate of 30 centimeters. So you need quite accurate clocks. And fortunately, we have those, which are atomic clocks. And atomic clocks are, their oscillator is based on an atomic transition of a certain element, for instance, hydrogen, or more commonly used as cesium. And there's a certain transition in the cesium atom that emits a radio wave, and the frequency of that radio wave is exactly this, almost 9.2 gigahertz. And the atomic clock measures that frequency and uses that as the oscillator for its clock. And this gives you a time resolution of 1.1 times 10 to the minus 10 seconds. So this is a very accurate clock. And these atomic clocks used to be very large, like, I don't know, like a tabletop thing. But recently, I think 1 or 2 years ago, they've become available as chip-scale atomic clocks, which is about, here you see it compared to the size of $1. And this is ideal for our CubeSat. So now we actually have the technology to have an atomic clock in a CubeSat. And to show a bit more how sensitive GPS actually is to time, I'd like to talk about time dilation. It's Einstein's theory of special relativity. Basically, is this equation, and it tells you that for an observer moving very fast with respect to an immobile observer, his time will go slower. And in fact, satellites of the Earth GPS constellation, they move at 14,000 kilometers per hour, and it is fast enough that the clock of the satellite ticks about 7 microseconds slower a day than a clock on Earth would. But there's also general relativity. And general relativity tells us that the closer you are to a massive object, the slower time will go. Maybe some of you have seen the movie, what's it called again? Interstellar, exactly, where they go to a planet near a black hole, and when they come back, the other guy is 50 years older. So time moves slower when you're nearer to a massive object. And since the satellite is higher up in Earth's gravity well, so farther removed from the Earth, time goes actually a bit faster for the satellite. about 45 microseconds faster per day. So this leaves you with a net 38 microseconds drift in the satellite clock every day, and if you would not correct for that, you would have a compounding 11-kilometer offset of your GPS position every day. So this is clearly something you need to correct for. And what they did is that the carrier signal of the carrier signal the satellite sends out should be at 10.23 megahertz. That's what your receiver expects. But instead, it's at 10.22999999543 megahertz. So this tiny difference in frequency, which is intentional, corrects for this this time drift. So as you can see, without the theory of relativity, your GPS would not work. So now I've explained what GPS is. I'd like to explain how we get to the GPS constellation. And before I do that, I briefly want to introduce the concept of an orbit and how we characterize an orbit. So to stay around the massive body, to prevent the spacecraft or a satellite from crashing into a celestial body, it has to keep moving. And you can imagine that if it goes in a circle, there's a certain velocity and a certain distance from the planet, that the centrifugal force of the satellite offsets the gravitational force, and that's a stable orbit in a sense. So these orbits are usually elliptical or circular, and we define them by the orbital radius, which is the distance from the center of the celestial body to the orbit. And the other important one is the inclination. So if you have the planet or the moon is turning around on its vertical axis, and it has an equatorial plane. And you can imagine orbits that are at an angle with that to that equatorial plane. As you can see here, that's the inclination I. There's a bunch of other parameters which are not as relevant for us now. The other thing is that you can also imagine that if you have an orbital plane at a tilted angle, you can also turn that around the vertical axis. So that's how an orbit is defined relative to the celestial body you're orbiting. And so we want to have a constellation of GPS satellites. And what we want is we have full coverage. We want to cover the whole globe, or the whole moon in our case. So it turns out that the best way to do that is with a Walker Delta constellation. And they are defined as follows. You define the inclination. Basically, it's a Walker Delta constellation consists of one or more satellites in one or more planes, which have the same inclination, and they're equally spaced around the azimuthal direction. So you define I, which is the inclination, N is the total number of satellites, P is the total number of planes, and M is a number that basically relates the phase between satellites in two orbits, so they might be out of phase a bit. So with these numbers and the orbital radius, you basically define a satellite constellation. So now the question is, how do we determine which orbital radius and how many satellites we use? So the thing is, the requirement we have is you want to have full coverage, and we want to see at least a minimum of 4 satellites at every point on the globe at every moment in time. That's our requirement. And there's many ways to do it. And of course, we'd like to use as little satellites as possible because that makes it cheaper. I could put 1,000 satellites and for sure have coverage, but that's not an efficient solution. The farther away I put my satellites, the less I need, because each satellite would see a larger part of the moon. But the problem is that CubeSats only have limited power on board. I cannot build a huge antenna, so there's a point that I'm too far away from the moon for my signal to reach the moon surface. So for instance, if you imagine that you would have 10 watts of antenna power on board of the satellite, and you would have the antenna broadcast almost isotropically in every direction, so you don't have to point the antenna, and the user will be using a commercial GPS receiver, and they have a minus 160 decibel watt threshold, so the signal has to be larger than that for a GPS receiver to accurately receive it. So now you can ask yourself, you can calculate what's the loss over this distance, the free space path loss. So what's the maximum distance that my 10 watt signal would still reach the moon above this threshold? So the free space path loss is something you can calculate like this. It has to do with the inverse square law, the fact that if I go farther, I have a spherical surface that I have to distribute my power over. And it's also related to the wavelength, or if you will, the frequency of the wave, of the signal I'm sending. So you can express this in decibels, which makes it easier to do the calculations. This is a constant. For F, we use the 1575 megahertz signal. This is the frequency of the conventional GPS signal. And basically what you want to do is with the antenna power minus this loss, this has to be larger than minus 160 decibel watts. And it turns out that you get almost the maximum altitude is from the surface to your satellite is about 2,700 kilometers. If you take into account the radius of the moon, you get to an orbital radius of about 4,400 kilometers. So this is our maximum. But there's a but, because this calculation is basically only considering a satellite directly overhead. And in fact, if I want to make use of the satellites, I want to be able to see satellites up to a certain angle above the horizon. This angle is the elevation. And so you can do some algebra and you get this formula, and you see that this maximum distance, it's not h, the altitude, it has to be smaller than this distance we just calculated, but actually the distance x, which is slightly longer. So if you take that into account, you get an orbital radius of about 3,400 kilometers, so your satellites need to be closer. Or you can also say, well, maybe we can put 20 watts on board, and then the previous solution would be valid as well. And 20 watts is something, considering the recent improvements in photovoltaic so solar cell technology. This is something that might be possible in the near future. So we went for the 20 watts, and we settled on an orbital radius of about 4,000 kilometers to have a bit of a margin. And in the end, we chose a Walker Delta constellation with 4 planes, so these 4 colors, 28 satellites in total, so 7 satellites per orbit. And this number 6 is phase spacing, which basically means that it's spaced equally around in their orbits. And it looks a bit like this, and it doesn't tell you too much. Each of the dots is a satellite. But what we did is we calculated from each point on the moon how many satellites will be visible at that point. And you get a map that looks a bit like this. It looks more like a Picasso or art than a graph. But so what you see here is the longitude from minus 180 to 180 degrees, and here the latitude from minus 90 to 90 degrees. And the color bar here tells you the amount of satellites visible at that location. So there's a minimum of 4, which is these areas here around the equator, and they range up all the way 5, 6, 7 to even 9 satellites visible here and here. So you can see with this constellation, at this moment in time, everywhere on the moon surface, you can see 4 or more satellites, which was our requirement. And you can simulate the satellites moving, and then you will see that these patterns kind of shift, but you will see that everywhere there's still a minimum of 4 satellites. So this constellation will be a solution. This is the one we chose. So now we have our mission. We know we want to have a constellation. The thing is that to get this constellation, the satellites have to go from Earth to the moon. Then they have to change their inclination, because from Earth to Moon is basically in the equatorial plane of the solar system, also of the planets. So you have to change the inclination, and then possibly they would have to correct their orbits during their lifetime, because in first approximation an orbit is stable, but in the end you have a lot of perturbing forces like solar radiation pressure. That's the light of the sun pushing on the satellite, which is ever so minute but compounds over time. You have the gravitational force of secondary bodies like the moon and the sun pulling on the satellite, and that perturbs the orbit. And also the moon is not very spherical, it's very rocky. There's locations where there's a higher density of mass and lower density of mass. So the gravitation locally changes in the orbit, and these are all kind of perturbing forces that the satellite has to correct for. So for all these maneuvers, the satellite needs a thruster. So the question is, what kind of thruster are we looking for? And the thruster needs to be cheap and simple, so we can make 28 or 30 or how many ever we want from it, and make it cheap. It has to be small, because it has to fit in the satellite. It has to be efficient at low power, because the satellite is limited in power. And it has to have a high exhaust velocity, so that we use as little propellant as possible, because we're also volume limited. And furthermore, it has to be robust, because it will have to keep working over a span of 10 or 20 years, however long you want this constellation to be operational. And it has to be able to switch on and off. So these are all requirements for our thruster. So in the end, we settled on quite a new technology. It's called the Electron Cyclotron Resonance Thruster. You see a schematic here. And basically it consists of a magnet, which creates this magnetic nozzle, which is the curved field lines of the magnetic field. And this is kind of a coaxial setup. This is like the outer shell, and this is the antenna. and you introduce a microwave signal here, which is illustrated as the red line. And the principle it's based on is electron cyclotron resonance heating. And what this means is that, as Sarah already said, a charged particle, in this case an electron, in a magnetic field has a tendency to start to spiral around the magnetic field lines. And this spiraling or gyration, there's a frequency that is particular to that motion. Now, if you send microwaves into the plasma exactly at that frequency, you have a resonance, and the electrons really efficiently absorb the microwave power. So this way you can heat the electrons, and the hot electrons then expand out along the field lines, and they drag along the positive ions with the electric field, as Sarah just explained. So this technology is in its developmental phase. It's already working, but it's not yet optimized. It already has quite impressive characteristics. It works at about 30 watts now. It produces 1 million of thrust and has 1,000 seconds of ISP, which basically means it has an exhaust velocity of 10,000 kilometers per second, 10,000 meters per second, sorry. And the efficiency is about 17%, which is quite impressive for such a small thruster. So this is the technology we used. Here you can see it. It looks very pretty. This is operating with xenon. This is basically the thruster, and this is the plume. This is with CO2. That's another characteristic of this thruster. It can basically run with any propellant. So here we fed it different propellants. We didn't measure the different efficiencies of the different propellants, but we are sure of it that it, no matter what, looks very pretty. I think I also have one with nitrogen.
Okay, well, sometimes science is more art than science, Morty. A lot of people don't get that.
And so yeah, that's that. So we've chosen our thruster. We know our mission. We know where we want to go. But how do we get there? And how do we get there in a way that costs as little propellant as possible? So there's a way to do this, and that makes use of invariant manifolds, and that's an idea that's here very artistically illustrated as these tubes connecting several planets and moons. And before I can explain what an invariant manifold is, I have to explain what a Lagrange point is. And this is a concept from astrodynamics. Basically here you see a curved surface, and this represents the gravity well of the sun, and this represents the gravity well of the Earth. So when it goes down, the gravity is where it goes deep, the gravity is stronger. And you see there's these saddle points here, and there's 3 of them on the line connecting the 2 bodies, and there's 1 on each side of that. And in these saddle points, the sum of the gravitational, the Coriolis, and the centrifugal force in the system on a satellite is 0. So this is, in a way, if you could stay at that point, you would not feel any force, apart from some perturbing small forces. But you basically you could stay here. In theory, it's almost impossible to stay exactly at that point, but you can orbit these points. And that relates to the stable manifolds. So this is a graph, and here you see this is the L2 point. So here you see the L2 point again. This white circle is a certain orbit around this point. Here ME is the Earth, and M here is the moon. So what happens, you have these orbits around the Lagrange point, and they're unstable in a sense. So if you perturb your spacecraft slightly, it will depart from the orbit and drift away. And there's a whole set of solutions of trajectories that depart from the halo, from this orbit, which is called a halo orbit. So all these red lines are trajectories that you basically would take if you at a certain moment depart from this orbit. And these solutions are called the unstable manifold. And in the same way, there's also a whole bunch of solutions of trajectories that somewhere here go through space, and they latch on to this halo orbit, which is the stable manifold. So you have this tube of possible trajectories that go towards this orbit, and there's a bunch of trajectories that go away. So these are kind of, it's like swimming with the stream. So instead of swimming against the stream, you would let the river drag you along, and that's why you save energy. So in the same way, when you launch from Earth your satellite or spacecraft, you would try to latch onto one of these trajectories, let it carry you towards this orbit, and then when you're at this orbit, thrust a little bit to get away from the orbit, and then follow one of the red lines away from the halo orbit. So, and then you would do it in such a way that the unstable manifold trajectory that carries you away from the Lagrange point, you choose the one that at a certain section here, you can patch to a trajectory that would capture the satellite around the moon. So in that way, you only have to thrust slightly along the way to stay in these lanes, but generally get dragged along by basically the path of least resistance in the gravitational system of the moon, sun, and the Earth. So this is the theory of invariant manifolds. And so you can get basically an initial guess based on this, and then you can optimize this. So you get a control problem. And we have 5 state variables. So you have the position x and y, because we imagine this is all happening in the plane. And then the velocities x dot and xy, and the mass of the spacecraft. So those are the 5 states variables. And there's 2 control variables, which is the throttle, which is the amount of thrust I put between 0 and 1, and psi is the thrust angle. And what we optimize for is the final mass of the spacecraft. The larger that is, the less propellant I've used, so the better. And since the algorithm minimizes, you optimize for the negative of that value. So we've run this algorithm, and you get several solutions. We did one run for a satellite of 3 kilograms, and another for a satellite of 6.5 kilograms. And you will see that both of them take about 156 days. And the first one uses about 4.1% of the initial mass as propellant, and the other one 30.3%. And the interesting thing here is that the fact that not just the absolute, but also the relative value of the propellant used is so different between 2 different masses is a direct reflection of the rocket equation, which has this logarithm in it. Here's some nice plots, just to finish. This here you can see the mass decreasing as a function of time, and you can see the same for the 3 kilogram spacecraft here. This is a solution for thrusting. So you can see, for instance, that the 6.5 kilogram spacecraft is basically slowly thrusting the whole time, while the lighter spacecraft, here's a bump and then has 2 hefty burns at the end of a trajectory. And this is actually something that's more closely related to using chemical propulsion. This basically means that the thrust you have for the spacecraft is actually a bit too high with respect to the mass it has. So instead of thrusting continuously, as you would expect with electric propulsion, you actually do 2 short sprints. And this one is very messy. I'm not even going into it. This is a thrust angle. So this was the project we did for the competition. And I hope we've been able to explain it in a more accessible way to you. I hope you've enjoyed it. Usually I would give a summary now, but instead of doing that, we'd like to play a video because we think that exactly summarizes what we've just told you. So now we'll play the video, and I hope you will enjoy the video as well. Yes, no, it's not here. Yeah, big, double click.
Apollo 17, 1972, was the last time humanity visited the moon. 2 years from now, we will be celebrating the 50th anniversary of that feat. In the time since, the space race shifted from purely governmental and military enterprise to becoming a major sector in the world economy and a major contributor to the pursuit of knowledge that is science. But we never did manage to keep up the whole visiting other worlds thing, at least not in person. Today, we might be on the verge of changing that, and for future astronauts to explore worlds, new and old alike, new technologies will be needed. Major players in space are calling for a permanent outpost on the moon, a lunar village, if you will, both as a research station and as a stepping stone for deep space missions. Navigation around the moon will be just as crucial for explorers out there as it is here on Earth, and the thought of a Lunar Positioning System, or LPS for short, is not far-fetched. A Walker-type constellation using 24 satellites in 4 planes with an inclination of 60 degrees would provide GPS-style navigation with full coverage on the surface, even at the lunar poles. Such a constellation has an altitude of 2,262 kilometers, which allows for L1, L2 signals to be transmitted by a 10-watt antenna. These would reach the surface with a signal strength above the minus 160 decibels watt limit of commercial GPS receivers. But since we're going small, why not go all the way? With chip-scale atomic clocks, miniaturized ACDS and microwave generators, and small, highly efficient solar cells, the LPS constellation could be realized using CubeSats. Indeed, the visionary Lunar Positioning System is made possible thanks to the advent of these nanosatellites, together with careful mission definition, trajectory optimization, and one more key ingredient: microelectric propulsion. In order to arrive at the moon, we are focusing on the latest addition to the electric propulsion family, the Electron Cyclotron Resonance Accelerator, aka ECRA. The ECRA uses a microwave generator to ionize and heat up a plasma partially contained by a magnetic field. A magnetic nozzle then accelerates the plasma in order to produce thrust. It boasts some big advantages, such as no moving parts, no need for a neutralizer, and very competitive foreseeable specifications for the low power spectrum. About 30 watt input power, 1 millinewton of thrust, and 1,000 seconds of ISP. These numbers mean you get a lot of mileage on very little fuel, just what we need for this mission. Current efficiency of the ECRA is about 17%, which may seem low, but it's already competitive with similar thrusters such as the BIT-1 from Busek or the P4 RTF from Phase 4. The thruster efficiency is the result of 3 separate efficiencies: mass or ionization efficiency, divergence efficiency, and energy efficiency. We believe that we can act upon the mass efficiency for iodine propellant by optimizing the power-to-mass flow ratio in relation to the physical geometry of the thruster. Ideally, we can also obtain better energy efficiency by lowering energy losses to the thruster walls, by adapting the thruster wall angle, exploiting magnetic shielding. We expect that the efficiency for an optimized thruster could be about 30%, which is truly great for this power range. Finally, we use concurrent design for the propulsion system and the trajectory optimization in order to open mission avenues that might not have been thought possible until now. We carried out a non-linear optimization of Earth-Moon trajectories for a 3U CubeSat using the dynamic frame of the planar bicircular four-body problem. An impulsive maneuver of about 1.2 kilometers per second at geostationary orbit would inject the CubeSat into an initial transfer trajectory. From then on, it would rely only on its ECRA thruster to arrive at lunar orbit after 150 days, having consumed an amount of fuel of up to 15% of the CubeSat's initial mass. Of course, no-good mission analysis would be finished without a cost estimate. However, since CubeSats represent a paradigm change in the way we access space today, it is still difficult to provide exact figures. Our estimates put a price tag of about $10 million on the constellation cost, and an additional $20 million for launches, if upcoming dedicated platforms are used. For comparison, the initially estimated cost of the Galileo navigation system was $3 billion. Thank you for listening to our initial take on this bold lunar positioning system. We truly believe that the combination of new electric propulsion platforms and careful mission planning and optimization will open the way for exciting opportunities in the future, of which we hope to be a part of. Hopefully, the moon won't have to miss humanity for much longer.
Questions?
You said at the beginning of the talk that 30 small satellites are better than one bigger, but how do you think about the problem with the space debris? Because if you have, let's say, 30 microsatellites and everybody starts to send like a small piece of things in the space, don't you think that it's going to be difficult to make new launches?
The thing is that I think there's already a law which is not really thoroughly enforced, but everything that's launched now has to make sure it deorbits itself after 25 years after or 15 years after its own lifetime. But as you can see, actually putting propulsion on board of these things would make sure that they can deorbit, and you basically take that into account of your mission, that wherever they are after that lifetime, they have to use their thruster to either remove themselves away from the Earth or crash into the atmosphere. And for the moon, there's probably other places where they can go. So yes, there's a risk more, but I think since the space community is so aware of the problem of space debris, there is ways that you can prevent making more space debris.
Did you think about this in your project?
Not particularly. First of all, because for instance, this project goes to the moon and most space debris is in Earth orbit. Yeah. But yeah, we were aware of the fact that having a thruster on CubeSats is exactly a good idea because of that, the space debris problem, because current CubeSats don't have that, and yeah, basically it's a piece of trash floating around because it cannot move itself anymore.
Okay, thanks for your presentation. Please, in slide number 30, about the distribution of number of satellite.
Yes. 30 what? Sorry, Raj?
30,
Yes, this one.
29?
This one? or
No,
next?
no. Yes, this one. I mean, it's strange for me why it is not symmetry. For example, point minus 180 is supposed to be exactly as point 180 because this is the same point.
I think it is because you see this orange and yellow part. I think it should be. It's not symmetric, but it should be around. No, you should be able to close
Yes,
it. And
but
it is the case.
here it's not symmetry. I mean, if you see, for
It's
example,
not
the yellow
symmetric,
part,
it's not
yes.
symmetric, but I mean, this boundary should be the same as that boundary. Because
Yes, but it is not, I think.
that is the case.
Hmm.
Well, it's difficult to judge by eye, but as far as I can see, that's the case.
For example, the yellow part around minus 90 in the left.
There's what? There's a
Down, yes, this part, for example, it's not appear in the second. I mean,
this yellow part.
yes, this part, for
Okay,
example.
there is. There actually the small pointy part here. The thing is, the resolution is not too great,
okay,
and
okay.
also you're at the, I don't know, but yeah, it is.
Yes, because I mean, if you close
It should, yeah, it should be right.
Yeah.
And I think it is, but maybe it's not very. You can't. I think the fact that because you can see the resolution here is not too great. No?
Yes, yes, maybe it's a reason. Okay,
So that
thank
could be, but that it should be like this because it's calculated that way.
you. Okay, thank you.
Very attentive.
¿Alguien tiene alguna pregunta? Va.
Well, unless you.
I think I turn it off.
Thank you very much, guys, for your presentation. I just wanted to ask you if, when designing your constellation, did you consider to include chaser satellites or backup satellites? Because, for example, in the Galileo constellation, there are 10 satellites per orbital plane. 8 of them are operational, and 2 of them are for backup. So, just to know if you considered it.
Yes, that's true. No, we did not consider it because, first of all,
Well, it
we're
was like a first approach.
yes, we're not astrodynamics people, so that's the first thing. We just wanted to do a proof of concept, doing some first principle approaches, like just to show that it's feasible, that it's not completely insane to make a constellation with CubeSats. So, but yeah, there's much more things you need to consider. But going where I put 28 or 32 satellites, that's a small. That's not a big problem, especially not if they're cheap and small. Scaling it up is not an issue then.
Thank you.
¿Alguna otra pregunta?
Hi, thank you for your presentation. It was pretty cool. I'm curious about, have you ever wondered how many users could be using this system simultaneously? I mean, if that's its bottleneck or not.
Well, of course, now anyone, no? But our idea was like, since it seems like all the space agencies want to go back to the moon, our main idea that was maybe, I don't know, in 30 years, there will be like a lab, kind of a lab in the moon. So they will be really useful, maybe not for so many, let's say, human users, but also like robots going just around, and they will need in somehow to need what's the exact position or whatever. So I think it would be definitely something useful if we build a lab, a future lab in the moon. So
I'd like to add to
Christopher?
that. Yes, I'd like to add to that. For instance, there was one example. There's a Japanese mission, and they're trying to land something on the moon. And apparently, they have because it's not easy to land something. You need to, especially if you're doing it remotely controlled, you need or automatically. The spacecraft needs to accurately know where it is. And they actually informed us that having GPS on the moon would make it much easier for them to land, for example. So that is also users. And especially since we were considering radiating always, even inbound spacecraft would be able to use the GPS system at a certain point. And the other things you asked about a bottleneck, because if there's a maximum amount of users, is that your question?
Yeah, exactly.
Yeah, that's exactly the point with the, because since GPS is one-way communication, you're only receiving. So it doesn't matter if there's 50,000 people or one person receiving, because there's no, you're not communicating. You're just receiving, and you're doing your calculations on board of your device. So that's not a bottleneck.
Okay, thank you.
Do you think this lunar positioning system could be also used, for example, for the positioning of spacecraft traveling from Earth to the Moon, for example? Have you thought if this could also serve as a navigation system for this kind of spacecraft?
To see like 4 satellites to be able to have your position, you need to see 4 satellites. So probably there will be some points in space that you're able really to receive the signal, but we haven't done any calculations or whatever. So probably there will be some points where it could be also.
Maybe this could be also a good application.
The thing is, of course, I think it's only useful for spacecraft that get close to the moon, because since we're using CubeSat, you only have 10-20 watts. I mean, it will. What was it calculated? It was like 4,000 kilometers. No, sorry. The distance of the signal was almost 3,000 kilometers. So it will mean that in the other way, it's also 30. So there's a maximum distance. The signal goes about 6,000 kilometers away from the moon's surface. So only useful for spacecraft in that area, because otherwise you could do it with big satellites again, with big antennas, and then you could have it as a navigation point for other things. But in general, that wasn't the point. The point was to make it small, and therefore it wouldn't be useful for spacecraft.
But anyway, maybe for landing or launching, it could assist these
exactly
events.
For that, it's useful, yeah.
Thank you.
¿Alguien más? Bueno, si no hay más preguntas, bueno, muchas gracias, Sara y Mick.